I wish all the respected speakers, faculty members, and participants a warm good morning. Here, we have assembled again and are ready to commence the first session for the second day of Faculty Development Program at SSIPMT Raipur. To begin with the journey of knowledge and insight, I am grateful to have Dr. Kush Kumar Dewangan sir with us. Dr. Kush Kumar Dewangan sir works as an assistant professor at MITS Madanapalle, Andhra Pradesh. He has done his BE Mechanical Engineering from Government Engineering College, Bilaspur, Chhattisgarh. He also holds a MTech degree in thermal energy from NIT Roorkee and a PhD in mechanical engineering from IIT Kharagpur. He also has 8 research papers published in national and international journals. Sir, I would request you to take command and begin the first insightful session for the day.
Okay. Thank you for a brief introduction. It's audible?
Yes, sir, it's
Yes,
Hello?
audible.
please.
Okay. Okay. Very good morning to all. Uh, I, Kush Kumar Dewangan, is Assistant Professor in Madanpalli Institute of Technology, Madanpalli, Andhra Pradesh. First of all, I would like to thank this institute, Sri Sankaracharya Institute of Professional and Management Technology, to organize such kinds of event to spread the knowledge or communicate between the same area of people and other area of people also. We can communicate and we know about the recent trends in thermal engineering, as well as we also know the recent trends of thermal engineering is how is interlinked or connect with the other technology or another area also. Uh, and I also like to thank Dr. Mayank Sharma to giving me this opportunity to give my research work and present in front of this platform. And thanks to all the members, those are associated with this event, and also this participants also. Uh, if any question in the participants, they can ask in between the presentation, or they can ask in end of the presentation. No issue. Just a minute. Slide is visible.
Yes, sir.
Yes, sir, it is visible.
Okay. Okay. Uh, these events, I just want to highlight this thermal engineering. Nowadays, thermal engineering is more complex. The remaining part is the research. If you're going by the research, that's much more complex. That's because the easiest things we already know and be very well in fundamentals. Then is a nowadays that's the research is going to very complex natures. Like is a combustion phenomena that is very difficult to understand and even the simulate and the experiment. Still, we are very far from this kind of phenomena. That's today's I'm going to talk about this. Just a minute. Sorry. Sorry for interruption. That's exploration of flashing in stagnant liquids and analysis of flashing driven natural circulation loop. Before going to the topic, I just want to highlight that flash. This presentation contains three parts. If time permit, I will cover all three parts, or at least I will cover the two parts. First, the complete things. This time, if you're any researcher is thinking about any research particular area, then you also think about that experiments, numerical, and last is analytical study. If complete package is there, then we can say that this a research or these works are good. Then I just highlighting these things in flashing in stagnant liquid and analysis of flashing differential circulation. This is the first part is the experiment, second is the numerical modeling, and third is the application based. That's flashing. We can how this flashing is associated with the natural circulation loop. Okay. Okay. This phase change process, if you see the phase change process, we already studied in heat and mass transfer at the undergraduate level. The phase change process is a boiling, condensation, like that. But liquid to vapor phase change, if you are saying the transformation from liquid to vapor phase, it's three driven, or maybe transfer from one phase to another phase may be possible in three ways broadly. First one is a temperature driven. That is a very simple. We already know about the boiling. If liquid temperature is, if boil the liquid in a pan, its temperature reaches to the boiling point, it start a boiling, bubble formation, different regions of boiling. That is a temperature difference. Due to the temperature difference, so that is the heating, its boiling start. Second is a concentration difference. There is a concentration difference, that is called the evaporation. This boiling and evaporation, these two are very different. Okay, this boiling means bubble formation, that's different regimes are nucleate boiling, film boiling, this kinds of things. But evaporation is no bubble formation, only evaporation, only phase change due to that concentration driven, or uh, we can say that is another cause is also associated with the concentration driven to cause of this evaporation. Third category is the pressure driven, where due to the pressure difference, this phase change may be take place. That's very well. Point is one we already know about in the fluid mechanics, that is a cavitation. The cavitation phenomena we know that is a turbine and pumps, that is a bubble formation and bursting due to the when pressure is reached to the below saturation pressure or the vapor pressure. Due to this pressure variation, the cavitation may occur. The last one is your it's a flashing. This is quite similar to the cavitation, but there's some difference between these two. The flashing is also by the pressure driven. Means it's due to the pressure difference, this phase change will be take place. Then my area is highlighting about this flashing, how flash evaporation is there, because this topic we are not covering in undergraduate, even postgraduate course. And this flashing is much more related with the two-phase phenomena, or is a multi-phase flow. If anybody studied in a two-phase flow or multi-phase flow, then they can see about this flashing. Flashing is not like if your undergraduate students is from other department, they see the what is flashing. It's not like a light flashing. Okay, it's a phase change phenomena. That's we call flashing. Okay, then what is the flashing? Flashing is a more common terms. It's used different words for this phenomena. That's flashing, flash evaporation, rapid boiling, front propagation, adiabatic phase change, like that. Because in this process, we are not providing any kind of heat for the phase change, because this is a pressure driven. The flashing, then, if you are taking one common definition for this flashing or flash evaporation phenomenon, is that when liquid is in a saturated state, okay, like liquid is in a saturated or it's a subcooled state, when suddenly depressurized, the liquid becomes superheated at that reduced pressure. For the example, if a liquid is in any pan is 80 degrees centigrade atmospheric pressure, if we reduce the pressure by any method of this in water in the pan is like 0.5 bar. It's a 0.5 bar the saturation temperature nearly 60. I am not know exact value, but it's just like near to 60. Then as the initial temperature is 80 degree and is a saturation temperature at reduced pressure is a 60, then liquid becomes superheated. It's a non-equilibrium, or is a there is an unstable state. Then liquid what will do? That liquid gain the thermodynamic equilibrium by the rapid evaporation. This kind of phenomena we call the flashing. Then again come back to the definition. When liquid initially is saturated state or subcooled state, it suddenly depressurized, the liquid becomes superheated. Then to regain the thermodynamic equilibrium state, its rapidly evaporation will take place. That's called the flashing or flash evaporation. The flashing is something similar with the cavitation, but is not exactly same as the cavitation. There is a difference between the cavitation and flashing. That's we can see in this plot. That's the pressure versus distance. If this plot we can see for the any valve or system where liquid is flowing on through the valve, then its pressure is decreases, and this dotted line is showing is the vapor pressure line. It's a boundary line for the particular operation. Then In cavitation, is when the pressure is goes below the vapor pressure, that's bubble form, and by the collapsation or bubble bursting, that pressure is again recoverable and it's reached above the vapor pressure. That it's not the some phase change will be take place, bubble formation, then again it's come to the equilibrium state, we can say. But in the flashing, it's not like that. It's when the pressure is goes down, it's not recoverable. The bubble formation, bubble bursting, also all the things are there, but pressure is not recoverable. That's the main difference between the cavitation and flashing. Another difference is that cavitation we already always seen in the flowing fluid. Okay, that is the flowing fluid means to flow through the valve, flow through the any that's pump, turbines, or any components. But in flashing, we can see flowing as well as a stagnant liquid. Okay, that's two cases we can see this flashing phenomena. Now, the flashing, why we need to study this process? Yes. That the process, so many applications are there, and that is starting from the desalination, that's the purification, or purification we can not. There is a conversion of this saline water to the drinkable water. There's a maybe the future requirement is there due to the lack of this drinking water. Okay, that's this desalination process is based on the flash evaporation. Another application is the spray and atomization. The spray and atomization, it's like in internal combustion engines, this they used atomization. That's nowadays is just much more interested to better atomization, better combustion process. This flash evaporation is also help for this atomization process. Next is the medical industry. Also, we use the flash evaporation. That's in nebulizer, inhaler. This is the medical industry is very rich now. Okay, that's then this flash evaporation also. This is one main phenomena for the spray formation. Okay, the nebulizer inhaler that is very well this is utilized in patients that's this affected by this or facing problem with the inhaling system. Okay, that next is a power and cooling cycle. That's we already seen. There's the geothermal flash power plant. There is some kind of evaporation process that they use the flash evaporation like that. And last is your one point is the food industry. There are different types of that's just like for example here the milk to convert the liquid milk to the powder. How this is possible? This is can possible with the flash evaporation. It's not continuously boil it and we solidify the milk. No, it's the liquid milk is sprayed into vacuum chamber and it's water or whatever the water available on the milk that's evaporate and the solid particles coming down. That is the milk powder. Similar to the food industry, also used in the wine manufacturing, the good quality of wine from the grapes is produced by the flash evaporation phenomena. And these applications are not limited up to this. So many applications are there. Even the high cooling or fast cooling rate, the flash evaporation is also preferred. But this maybe take some few years to come in our normal life because this flash evaporation is very complex in nature and but is a very fast result. It's a very fast cooling application. Within the fraction of second, we can decrease the 30 or 40 degree temperature of the any heated parts. Next, this flashing phenomena is not always beneficial to us. Okay, it is not always that flash evaporation. We are studying the flash evaporation. It's giving the number of application. No, this phenomena is causes as some critical issues and hardwares also. Then for understanding is very important. Either we can prevent the accidents or we can utilize the things. Just like a knife invention. Okay. This phenomena we need to study because this application as well as this avoid these kind of accidents like it's a loss of coolant accident that's very dangerous or that's a very huge accident in the nuclear power plant where the liquid means is flowing for the cooling liquid is circulating in the pipe. It's a very high pressure in a very high temperature. Any cracks in the pipe, just like it's a liquid is flowing in the it's a 50 bar just for example, and it's any crack in the pipe, there's sudden blast. Then is a loss of coolant accident, that's called. Then volatile liquid accident. Volatile liquid accident, that it's a very common, but it's a very rare. That's a blasting of LPG cylinder in house. Okay, that's a LPG liquid petroleum gas. We compress it, and means gas is compressed in the cylinder and in the form of liquid is stored. Okay, if any cracks on that, it's not possible. But many cases blasting, we heard about the blasting in news, that LPG cylinder blast. That's a blast is very drastic in nature. This blasting is also associated with the flash evaporation phenomenon because it's a very rapid expansion process. Is there any cracks or any by any medium that's happens, that liquid come out from the cylinder with the uncontrolled manner, that causes the blast. And if the liquid is stored in the container that is flammable, then this problem go arise very critical. Okay. The next is a damage or relief valve. The cavitation is damage the relief valve, we know, but this flashing also damage the relief valve or any kinds of control system, the flow control system. If the heat is associated, temperature and pressure changes are associated, that flashing phenomena may occur in that area. Okay. Next is similar to the volatile liquid accident, the liquefied gas pipeline also rupturing. That's a cause of very drastic accidents. And this flashing phenomena is also affect the natural circulation loop. Hence, it's a instability. That's natural circulation loop is used in a nuclear power plant and as in a solar heating system and some other cooling application. We also use the is a natural circulation loop. And this cooling loop is in this circulation loop, this flashing is there. It affect the performance or flow characteristics of natural circulation loop. Okay. With that, just I want to highlight this one specific. The flash evaporation is very broad. I just covered the one part. Is that there's a flashing front and nucleation sites about that. Okay. So before going to the main experiments, we see the what is the flashing. PV diagram, that's the pressure versus a specific volume diagram. For water, we very well know the saturation curve, liquid phase to liquid vapor phase, and is a vapor phase. Critical point, saturation lines. Okay, and till this undergraduate, we already seen these things, but the insight that something we are missed in undergraduate book, that is here. That if isothermal line, we know that in the PV diagram for particular, we are taking the water, the isothermal line is here. This is a constant line, it's going down. And we know that it's reached to the saturated liquid line. It's in liquid vapor phase change process, temperature as well as pressure, both are constant. Then it's coming here to the vapor side. Okay. But in this region, the liquid region and the vapor region, in these two regions, there is an unstable region. Okay, that's why we call the liquid vapor zone or is a liquid vapor dome, like that. But in this region, if you very deeply, we can see in this region is the line is not straight. Line is going, this isothermal line is going down, and it's reached to the one minimum point. Then it's again increase, and then it's curve like things are there. It's not straight. But for simplification process, we assume that, or this, if you are neglecting the minor things, then we see that as a pressure and temperature both are constant in the phase change process. But the actual things, if you're going very details about this, about the physics of this, then we can see that this isothermal line is not straight, it's a like curve. And this region, okay, then this outer, we know that if my cursor is visible here. Yeah. So then this region, this line we know that is saturated liquid line. This line we know saturated vapor line. Within these two lines, two more lines are there. This line near to the saturated liquid line is called liquid spinodal line, and this side line is called the subcooled, it's a vapor spinodal line, and this left side shaded region is called superheated liquid, and this side shaded area is called subcooled vapor. And this flash evaporation is much more associated with this superheated liquid region. This region, this shaded region is highly unstable. Okay, that's why we are not studying in undergraduate and we are not thinking much more about that. Okay, but if you're going for the research, then we have to see in this area also because this is very critical. Then if you are talking about the flashing process, then is a isothermal is a line we denote by the isothermal line is a liquid in initially saturated state, suddenly depressurized. Then suddenly depressurized means it's quickly depressurized. The temperature is not vary that much because it's a fast process. Then we follow the isothermal line and it's reached to the point 2. We think it for particular time, we think it's reached to the point 2. That point 2 is coming in within the superheated liquid region. That is very high, is unstable. Okay, liquid it's not staying at same state. Then its liquid start to regain the equilibrium condition. Then for the reaching to the equilibrium condition like 0.2 to 0.3 or 0.2 to some point in the liquid vapor mixture at particular this pressure, that's called flash evaporation. And this a process of evaporation is very rapid and many times if condition is controlled, we can see the one flashing front or evaporation front or we can say the boiling front here. Okay, then if just giving the example, okay, we can see that experiment. Before going to the experiment, we can see that what is the different region. Just like one tube is there, okay, and this side is a liquid vapor mixture that is called the two phase, and this side is the bottom side is a superheated liquid. That's a liquid state. Within these two, there pressure difference. This side is a low pressure region, and this side is a high pressure region initially. Okay, during the propagation, there is a not that much pressure difference. Okay, and this region, if you see that is in this interface. Okay, and this interface is called the flashing front, evaporation front, or boiling front, and it's similar kinds of we can if you analogy we can use for this flashing front as a flame front. The flame front, what will happen if you consider the one tube and filled with some gas or liquid, flammable liquid or gas, you will start the burning from one point from top. That's one. There is a burning start and form the one flame and is propagating. But how is propagating? It's propagating with unburned gas or unburned fuel, and it's produce the burned product. And this one front is propagating or moving in the unburned fuel. And this is called the flame front. Similar to that here also, that is one evaporation front is propagating the liquid, ejecting the two-phase mixture. And this, why we need to study for this flashing front. This is first of this is for the fundamental understanding of the phenomena. If any liquefied cylinder or compressed liquid cylinder is blast, the how evaporation will take place, how much the evaporation rate, how much the mass flow rate, okay, and this flashing front is one systematic, okay, this is systematic way to analyze this kind of accident. Okay. And now we come to this process about the gas dynamics aspect, okay, because these pressure changes are there, and then it's not only associated first one is this. If you see that this arrangement is a one vacuum chamber and one liquid container here. This liquid container is a high pressure. We can consider as atmospheric pressure. One vacuum is just like a 1 millibar like that. And we will separate these two chamber, high pressure and low pressure chamber. And high pressure chamber is with the liquid in equilibrium condition. Now we separate these two by the one diaphragm. Okay, one restriction between these two, one diaphragm is there. Once the diaphragm is captured, just like a shock tube experiment, many shock tube experiments are like that. It's a diaphragm they used for the experiment, shock tube experiment, and this kind of also. Then once the diaphragm is captured, the different waves associated with this propagating. In high pressure chamber,
Excuse me, sir.
expansion wave is propagating. And the
Sir, your
evaporation
presentation is
front
not visible
is
on the screen.
following the expansion. Yes. Okay. Just a minute.
Sir, your presentation is not visible on
Okay.
the screen.
Sorry.
Dear participants, there is a network issue from our speaker side. Please stay with us on the meeting. He will be joining soon.
Now it's audible.
Yes, sir. Now it's clear.
Okay. Okay. Sorry, this network fluctuations are there. Okay. Then this all the waves we can see here, that is in time versus space plot, that in low pressure chamber compression wave is propagating, or compression wave or shock wave we can say, in and then one contact is continuity is following that. In high pressure chamber, expansion wave is propagating or is moving. Then and its evaporation front is, or evaporation wave or boiling front is following the expansion wave. Okay, this is a very brief about the gas dynamics aspect of this flashing front, flashing phenomena. Uh, this, this phenomena, this flash evaporation phenomena is not only with the thermodynamics, is also going to the gas dynamics. Different waves are associated, different thermodynamic phenomena, even the multi-phase phenomena is also associated. That's why it becomes very complex. We cannot analyze all the things. We are picking some things from the gas dynamics aspect. We can solve it, or we can solve by the thermodynamics aspect. Okay. This phenomena is, if the liquid is suddenly depressurized, maybe different phenomena may be possible. I just listed this phenomena. If liquid becomes superheated by sudden depressurization, and nucleation, how evaporation will take place. That's maybe one possible. That's no bulk nucleation. Nucleation is the first stage of formation of new thermodynamics. Okay. And there is no bulk nucleation, no evaporation front. That may be possible. Second case is a pre-bulk nucleation. Okay. Pre-bulk nucleation, and nucleation may be start from the bottom end of the tube, then no evaporation front again if nucleation is start. Okay, this may be clear after if you're seeing this experiment, then this may be clear how different types of evaporation may be take place. If nucleation in the side wall or bulk of the liquid, partially propagation of evaporation front. The objectives, I just want to cover here, the experimental investigation of flashing current propagation at different inclination of the tube. Second is a numerical simulation of flashing current in the presence of nucleation site. What will happen if nucleation sites are present? And third is the application based on analytical study or analytical investigation of flashing driven natural circulation in single riser natural circulation, both like single riser as well as we already studied with the two riser. The first one is experimental investigation. For experimental, if you're seeing the experimental investigation, the background, if you're seeing that is this process or phenomena is already discussed nearly 1962. Okay, the Turner is observed that this by visualizing the experiment, he find out the flashing front is there and it's propagating in the superheated liquid. And after that, the continuous research is going on. This is due to advancements of the high-speed camera and the better measurement system. The researchers are more interested on this area to understand or to find out the physics about this process. Okay, the continuously studied and different parameter studies also is going on. That's how, what is the effect of diameter, what is the effect of degree of superheat, what is the effect of this inclination, like that. But there is no systematic study about the inclination. How, if tube is inclined, and what will happen? Because we know that is a liquid flow in a horizontal or vertical tube, the phenomena may be different. And there is if two-phase and boiling process, then phenomena is entirely different, because the different flow regimes we can find out here. That's why. This process is phenomena is already studied recently. This is up to 2017. Even next, I made this slide up to that 17. But this is the process. A study of this process of phenomena is still going on. This is still active. Okay. And this, if you're seeing the literature review, that I found that the water is less popular in this particular type of experiment, because the experiment with the water is very complex things, because water offer number of nucleation sites, because number of impurities are there, number of gas dissolved in the water. But particularly this, we are in earth, and water is our surrounded, and in most of the application water and air we are moving around. Our application or experiment is water and air. That's why I choose the water here to perform the experiment. But the water offer undesirable nucleation. That's a number of experiments is tried to suppress this nucleation site. And the second is the complete visualization. This process is a very very complex, and is very fast. And the complete visualization of propagation of water is here. And next is the effect of inclination. That's many people try it, but it's not up to certain levels. What is the effect of particular inclination of the tube on the flattening front? Okay, then this is the experiment setup. In this particular experiment setup, we made like a shock tube experiment, but slightly different because we are using the water here. And this, we can say, there is a high pressure section, is called driver section, and this is low pressure section. And we will separate these two by diaphragm. And similar things here. This here we used borosilicate glass tube. The diameter inside diameter is 22 mm and outside is 26 mm. And the length is 50 centimeter, is a half meter nearly, and filled with the water is 45 centimeters. Then this much long tube we used. And this tube is filled with the water. Okay, that's a clean water filled with this, and maintain some temperature by circulating the water bath. Okay, this water is circulated. One jacket is there, and water is circulated in the jacket to maintain the one constant temperature for experiment. And this part is your high pressure. High pressure, we can say that is atmospheric pressure is high pressure, because the low pressure section is nearly 13 millibar. That's why we have 1 atmospheric pressure, we can say high pressure. In the low pressure, it's a large vacuum tank, okay, or reservoir, we can see. And this volume, if you compare this glass tube and this reservoir or tank or vacuum reservoir volume, is nearly it's more than 150 times its volume. Nearly it's many times it goes to 200 and 300 times compared to the volume. It's a very huge size. It's 30 centimeter in diameter. It's 1 meter in length. And this vacuum reservoir is connected with the vacuum pump to maintain the desired vacuum in this. And this side is a low pressure and this side is a high pressure. These two different pressure zones is separated by the one rupture mechanism, or we can say the diaphragm. Okay. Next is for the measurement purpose, we use the pressure transducer thermocouples to measure the pressure at the top of the tube as well as the bottom of the tube, but for that bottom measurement is a much more complex. That's why we use a different setup for this. As the process is complex and it's very rapid, that's why we use the high-speed camera to capture the phenomena. Okay. This is a rapturing system. We introduced the rapturing system. It's a new kind of rapturing system, very cheap and is effective. We can say that if you're seeing the mechanical rapturing system is a very complex mechanism out there, but there like complex mechanism there, and this is a very simple thing. We used plastic diaphragm. That's commercially available, the polyester sheet or a transparent sheet, plastic sheet. We cut out in a circular shape and fit in this here. Here is a two collar. Upper collar is connected with the vacuum cylinder and lower collar is connected with the tube. That's borosilicate tube. And in this between, there's two flanges, upper and lower flanges, and between these flanges there is a nichrome gasket we fit, and this plastic diaphragm is inserted in this between the gasket. Okay, and just putting one nichrome wire for the heating. And because we use the plastic diaphragm for rapturing of the diaphragm, we can use the mechanical system, but we used here the heating system, we just put it the one coil of nicron wire and just put it, just supply the electric power so that nicron wire burn and it's a plastic diaphragm rupture. Then communication is established between the high pressure and low pressure channel. The test section, I just discuss about the two kind of test section we used. First one is a long tube. It's open in one end, closed in another end. But this kind of tube is restricted to measure the pressure at the bottom of the tube. We are able to measure the pressure at the top of the tube only. But this tube is giving one advantage to see the complete phenomena in tube. Second test section we designed to allow the pressure measurement at the top and bottom of the tube. Both places we can measure the pressure. That this tube is like a condenser part, okay, and we filled with the liquid, and liquid temperature is maintained constant by this circulating the hot water in the like concentric tube. Pressure transducer fitted at the top of the tube and one pressure transducer at the bottom of the tube. Okay. As this we use the water, and water offer number of nucleation sites. Okay, it's undesirable nucleation because we have to suppress the nucleation site for seeing the systematic propagation of lysine trans. Then we need to keep this pressure sensor. At this pressure sensor, this is a metal part. If the metal is contact with the liquid and temperature is going beyond the saturation, then it starts the nucleation site from this pressure sensor. That we not want. Okay, we have to suppress this nucleation site. Then we keep this pressure sensor or temperature, the liquid that's contact with the pressure sensor, the temperature we keep below the saturation temperature. For that, we use the ice water slurry to keep the temperature of this pressure sensor and nearby contact liquid below the saturation. Just like if the example of the experiment performed the 80 degrees centigrade of the water, okay, then we use we maintain the ice water slurry like is near to pressure sensor temperature is near to 5 degrees centigrade, so that it's not discharge the nucleation site. Okay, and this part is connected with the mechanism system, that is a lower pole. Okay. Next, the experiment is quite fast because this kind of a shock tube experiments like that is slower than the shock tube experiment because the evaporation process is associated with that. But the experiment is completed maximum visible whatever degree of superheat and tube diameters to be covered and depressurization we covered is the maximum is covered in 6 to 7 seconds. But the initial preparation is taking a lot of time. That's to maintain the vacuum pressure, to maintain the one constant fixed temperature of the water bath. It will take nearly 1 hour. After that, we boil the water for the degassing process. Degassing means is rigorously boiled and just apply the vacuum to remove the dissolved gases. That's called the degassing process. Initially, we use the clean water, that's the distilled water we use, so that there is less possibility of nucleation. Then we can fill the water in the tube, keep in the water jacket, maintain again the constant temperature, okay, fit out the rapturing system, then switch on the heating system. Same time we switch on the camera, so that the rapture, the film, the rapture means diaphragm is raptured, pressure communication is established between the high pressure and low pressure chamber, and the process is started. And same things we recorded in pressure as well as temperature, and the high speed camera, the phenomena is captured. Now, before going to the experiment, I just want to highlight this point here, that what are the initial conditions for the experiment. The initial condition for the experiment, we maintain the initial pressure, atmospheric pressure. Initial temperature we goes from 40 degrees centigrade to 96 degrees centigrade for the water. Okay. Because if you are going beyond the 96 degrees centigrade, the boiling will start itself in the tube. Then we cannot clearly perform the experiment. That's why we restricted up to the 96 degrees centigrade of the water, initial temperature. Reservoir pressure, the vacuum pressure we maintain, all the cases vacuum pressure we maintain 13 millibar. That's for 13 millibar, the saturation temperature of the water is nearly 11 degrees centigrade. Okay. Then is a starting process. This flow process we can divide into two kinds, two stages. First stage is a front formation, and second is the front propagation. Once that system is depressurized, when liquid is depressurized, okay, different waves are associated with that, and these waves are the expansion wave propagating the liquid phase, okay, and it's a transmitted passes through the liquid, okay, it's going to the bottom end of the tube, and it again is coming back to the surface of the tube. Again, is the process is going on. That is the reflection and transmission is continuously is going on. This pressure wave. Then same physical things we observe in the camera or captured in the camera is that as the system is depressurized, means diaphragm is ruptured. Within this 0.32 seconds, there is one nucleation site we can see in the middle of the tube, the water. Then there is a very fraction of time it's sprayed over the tube, and it will start the propagation of the tube. That is called the primary nucleation. And the nucleation far from the front zone we can say or we term as the secondary nucleation. Okay, the front zone nucleation we can say primary, or far from the front zone nucleation we can say the secondary nucleation. Now, before going to this the experiment with a different degree of inlet and or degree of superheat, or we can say the different inlet temperature or initial temperature of the water for all the tubes 50 centimeters. Here the lighting is not enough because this tube is very 50 centimeter length. Then this high speed lighting is very rare. Okay. That's why we use the LED light. Maybe this is like analysis is completed, but it's not that much visualize the clarity because the light fluctuation. But is the image processing made possible with using this kind of light, because it's a 50 centimeter high speed lighting is very rare in India. Okay. Then we can see here the different variation of effect of or phenomena with the different inlet temperature. What will happen to water initial temperature is 40 degrees centigrade, 50 degrees centigrade. And this one phenomena you can see the hand here shaking the tube. Many videos it's in YouTube. If you think that is one glass of water is kept in the microwave, it's increase the temperature like it's 120 or 130 degrees centigrade. Okay, and the water is taken out from the microwave, keep in the table, and just give one disturbance. Just keep one, put one spoon on that, it suddenly evaporates. Okay, this kind of videos are there. That is a similar thing. That's showing that it needs the initial disturbance for the many times it needs initial disturbance to start the phenomena. That's why many times we need to shake the tube, okay, by any method. Then there is to start the process. Many times it itself due to the depressurization, the pressure wave, the transmission and reflection, it will start the nucleation and it provides the disturbance for that. These videos are recorded at 1500 fps. This as a 1500 fps is sufficient for this. That's why we are not going beyond that. Otherwise, and this due to this long tube, as we can go very high speed. Okay. Now we can see that's all the phenomena except this 96 degrees centigrade. These are the systematic, that is evaporation start at the top of the tube and it's propagating in the bottom of the tube. And as the degree of inlet temperature is high, its propagation is speed, and you can see the two-phase mixture, that is the two-phase mixture ejection rate is high. Means evaporation rate is high. And evaporation rate is high means it's a propagation velocity of the front. You can see that all the fronts are there. This. Okay, the propagation velocity is fast. In 40 degrees centigrade, initial temperature of water is 40 degrees centigrade, the evaporation is very slow compared with the 80 degrees centigrade or 70 degrees centigrade. And all the process, we can see the different initial temperature. The front propagation is very irregular. We cannot predict the same thing. Even we can predict the speed of front propagation in some manner, but the front shape we cannot reproduce. We perform the experiment in 2-3 times, so we cannot reproduce the same thing. Okay, and I skip these things because some other videos are also there. Then after analyzing this videos, recorded videos analyzed in MATLAB, the image processing, we perform the image processing and take in the front state. And you can see that front state is a 96 degrees centigrade because some nucleation at the above. Okay, after that one systematic front is propagating that. And you can see that is a front state is very random. Sometimes the nucleation from the side, sometimes is a making different shape, and sometimes is a one liquid, a small liquid jet in the liquid, in the tube. That's why it's a very random and but the front velocity we can predict or we can find the some range. Okay. After analyzing of this image analysis of front location, we plot the front location with the time and the front velocity with the degree of superheat, and we can see that is obvious from the video that front velocity is higher in higher degree of superheat or higher in the temperature. Then next is that is a basic experiment. Okay, now is the inclination. What is the effect of inclination? Means if the cylinder we can keep is a horizontal or if the cylinder we can keep inclined, what will happen in evaporation rate? Okay, that experiment is there. Okay. Now you can see that is when the front formation start it's a not horizontal. It's perfectly horizontal. It's not possible because it's a long tube and 22 meter. Then it is we keep is a 5 degree incline, so that is the process will take place. And you can see that all the inclination, the front velocity or front propagation velocity is higher in the 90 degree. That is a vertical. Means if you're going to the going to the horizontal, that front velocity is the vertically is front velocity is the E. And for this, all the experiments performed is under the one constant temperature. Initial constant temperature is 80 degrees centigrade, and the vacuum pressure is nearly 13 millibar. And this, due to inclination, we can see there's a 5 degree inclination. Its evaporation is near to the surface only, and sometimes is due to the inclination, liquid interface is going to the bottom of the tube. Okay, and then this front shape and velocity. If we then after same things we can keep here that front velocity with the orientation. That different orientation, we plotted the front velocity and we seen that is the front velocity is increasing up to 30 degree inclination, and 30 and 45 degree is showing the nearly constant velocity. That we repeated the experiment many times, but is still there. After the 45 is following the another trend, so 45 to 90 degrees front velocity is increased. This front velocities may increase. It's a vertical that is easy to escape the two phase. Okay. It's easy to escape the two phase, like maybe, but it's required much more experiment to clearly say what is the effect of inclination. But still, we observe that inclination may affect the front propagation velocity. Okay, there is another experiment. That experiment is based on the one closed tube. Okay, this one tube is one side open, another side is simple like test tube. This experiment will be compiled or synchronized with the measurement, like pressure measurement. Pressure sensor we put in the top as well as the bottom of the tube. And same time pressure and as well as video recording, so that we can see that at the pressure, when pressure reaches to the lower, then what will happen in that experiment exactly. This experiment is performed in its initial temperature 70 degrees centigrade, and the video is recorded in 1500 fps. Now, first, that is the same thing. Liquid, initially heated liquid is kept in the tube. The circulated heated water, by the heating water, we can keep the heated liquid in the tube. Suddenly depressurize. The pressure measurement is showing here. This plot is the pressure measurement is showing there. Two pressure sensors we put. One is the bottom, at the bottom of the tube. Another is the top of the tube. It's showing here the two different curves. Red one is the bottom. Yeah, I think red one is the bottom, and blue one is the sorry. Yeah, blue one is the exit. The exit means is the top. Then how pressure is decreased, how pressure variation will take place, and at the same time we can see the flow process. What will happen in the tube? Okay, heated. Now again I just start it. Okay. The system is depressurized. Both bottom and the exit pressure sensor measure the pressure is decreased. You can see the pressure is decreased, but it's still not start the evaporation. At it reached the one point. Okay, then at that point it starts the nucleation at this here. That is one nucleation from the side wall, then it is spread over the tube and form the one evaporation front, and it's propagating. And at the same time you can see that these two pressure curves is parallel to each other. Okay, and it's parallel to each other means is the exit pressure and the bottom pressure is some deviation between these two due to this liquid column. But again I am just saying that process is not repeatable because this you can see the process is very complex, the random or is irregular nature of the liquid, the evaporation will take place, okay, and it's propagating in the superheated liquid. But successfully we suppress the undesirable nucleation by the degassing and proper killing of the water. We suppress the many undesirable nucleation. Even in a single day, 10 hours we perform the one experiment also like that. It's a very complex. If some nucleation sites are available or is present in the tube, that experiment is destroyed. Then this is pressure and temperature history. That's already been seen. That is the pressure. These 2 points, the bottom and the exit pressure sensor measure the pressure. Same time is the same temperature also. It's a temperature variation is also showing. And one important thing we find out from this pressure measurement and this by this image or recorded image, that delay time. Delay time means once the system is depressurized, liquid becomes superheated, but even that it's not a start the evaporation. That time between the depressurized and the starting point of nucleation, that point, the time duration we can say the delay time. And this delay time is decreases with increasing the degree of superheat. If you increase the degree of superheat, the delay time is decreased. This means very fast evaporation is there. There is no mathematical and even this physics is not clear about the delay time. If you increase, if liquid reach to be superheated, up to what time or what time duration you start the evaporation, nobody can. But if some by systematic experiment, we can say that degree of superheat, we can at least we can find the trend about the delay time. But I think it's a much more thermodynamics involved in this delay time. Maybe in future someone will say about the more details about the delay time, how the liquid start evaporation, at what time liquid going to evaporation which reach to the superheated state. Okay, this is the one image that is I'm showing here how nucleation site. If nucleation site is present in the tube, that tube in any point, how it will destroy the systematic analysis of displacing front propagation. At this point, we can see that is a starting point in the depressurized system. Some nucleation site at the top of the tube. Then it's push the liquid in the low pressure site. Then maybe the lack of nucleation site is propagating. Lack of nucleation site means secondary nucleation. Within the front is primary nucleation. Beyond the front is called the secondary nucleation. Okay? Then it's at this point, it is at the time is the 0.869 second, one nucleation site is visible. It's near to the bottom of the tube, and its growth rate is very fast. As the tube shape circular, it's formed the one long Taylor bubble shape. Okay, these terms are much more related with the two-phase flow. Okay. Then its long Taylor bubble form, and this long Taylor bubble pushes the liquid towards the low pressure side. Again, after pushing the liquid in the low pressure side, again one front is formed at the tail of the Taylor bubble, and it's again propagated. And at this point, this shaded area is highlighting the effect of this nucleation site. This effect. This is only the experiment is performed to see the physics. What will happen when the nucleation site starts. Then major findings about this, I think is one The major findings about this, that startup and analyzed in high-speed photography. Delay time is we observed, but we are not say mathematically or is a, fundamentally that delay time how to predict. We only analyze and we observe by the experiment. Next is to start the flashing front propagation and formation, it requires the initial degree of superheat. It's not like it's a 1 degree of superheat to start the formation of flashing front. No, it's a required one threshold point. This threshold point depends on the tube diameter, depressurization rate, degree of superheat, what kinds of liquids are used for the experiment. It depends on so many things. Then we see that the velocity of flashing front increases with the degree of superheat. As the degree of superheat increases, its speed increases, and its inclination towards the vertical. Means tube is vertical, front with speed is higher. And by this inclination, we see that the gravity may affect it. Gravity may affect the propagation. Maybe as this experiment is not very huge and it is still limited because this it's a time-consuming experiment. We have to suppress so many things, and in a day, if you're spending 10 hours, maybe it's in at your hand is nothing. Maybe that because of this complex nature of experiment. Then maybe in near future, I hope this so many the experiment is going on, and they give the physics about this experiment and different parameters affecting that. Okay, next is the numerical simulation of flashing front in the presence of nucleation. We already seen the one image where how if nucleation site is there, how flashing front propagation may affect. This is not directly related to the application. This is only fundamental understanding this how nucleation site is there. Then it indirectly affects the evaporation rate, or is like a sudden coming if in a tube nucleation side is there, then its nucleation side pushes the liquid towards the low pressure section. Then means liquid is added as this bulk amount is going out. Then it suddenly evaporates in outside of the liquid. Then if the again is a liquid is a flammable, then like is a blast maybe take. We choose the one-dimensional model because first we analyze the initially is a very simple. We start from the simple. That's one-dimensional. It's a not obviously it's a not a one-dimensional case, but due to complex nature, we start from the one-dimensional model. In future, maybe we will go for 2D and 3D to see the diameter effect or is it or the complete shape. This what we can say the tube effect or surface walls tube wall effect to incorporate in 3D or 2D model. Okay, but this time we only completed with a 1D model because it is still very complex because liquid one side is a liquid, another side is vapor, and there is a phase change. There is a highly non-equilibrium state. Okay, then lot of models available. If you are seeing that this problem is fall under the compressible two-phase flow. Okay, it's a two-phase flow model, but it's a compressible because the phase change and the speed is also associated with that. That's why it's coming. And we analyzed the speed of the sound, and we found that the two-phase speed of the sound is coming. It's much more the speed of the two-phase speed of the sound is higher than the speed of the sound. Then it's coming in compressible zone. That's why we choose this model. This model, multi-phase model, is different models available based on the number of equations they categorize it. 7 equation model, 6 equation model, 5 equation model, 4 equation model, 3 equation model, according to the number of equations. That's much more is the 7 equation model, 2 mass conservation, 2 energy conservation, 1 volume fraction. And 6 equation model, that is a 2 mass equation, 1 mixture momentum equation, 1 energy equation, and 1 volume fraction equation. Then I select this 6 equation model because 7 equation model is much more time consuming compared to 6 equation model, and the results are comparable. That's why I choose this. Anyone also can choose the 5 equation model. That is not that much, but 6 equation model is giving a reasonable result and is able to handle the metastable state. Metastable state means superheated liquid state is able to. And this kind of model we can choose to analyze the different problems like detonation, cavitation, shock impact, and flashing problem. And these we combined that's phase change. And for them for different property we need one equation of the state. For that, gases for the liquid we use the Stephen gas of gas equation of the state. These parameters are here, and this the experiment part is for particular for water. But now in this numerical model we choose the different fluids that is called the Dewangan. First we compare with the Dewangan, then we go for the water, because there's any model, if you start any model simulation, then first we validate it with the what is the available result. Then we have to go for particular thing. Then this fixed equation model is like that, is a three categories. That's with the hyperbolic part in mechanical terms, heat and mass transfer terms. This part is first equation is your volume fraction equation. That is how volume fraction is changing with that. Then two mass equation, mass conservation for fluid 1, fluid 2. This common momentum equation and two energy equation for each fluid. And this equation is based on the two fluid equation. It's one equation, one set of equation for the liquid, one set of equation for the gas. In between there is an interface. To handle the interface, this category will come, the mechanical relaxation and heat and mass transfer terms. Here the three relaxation parameters are there. The three relaxation parameters is your mechanical relaxation parameter, that's mu, and another two relaxation parameters is the theta and theta, that is the chemical thermal as well as chemical relaxation parameter. What is the role of this relaxation parameter? If suddenly we depressurize the system, just like it's a shock tube experiment, we've seen that as one side is the liquid, another side is the gas. We separate these two sections by the diaphragm. Suddenly rupture the diaphragm. Okay, then that liquid pressure is different, gas pressure is different. But in the interface, we have to have a one common pressure. It should be one common pressure. Okay? The liquid and liquid phase and gas phase have different pressure, but in the interface it should have a different, same velocity, same pressure. For that is a very fast phenomena. That's the liquid and gas phases have the same pressure at the interface. For that balancing is this, we use the mechanical relaxation, thermal as well as chemical relaxation. Then it's possible that as an interface it should be at least for the time being maybe phase change we can find out if the phase change will be there, or we can restrict to that's common pressure in the interface. Both phases have a common pressure at the interface, common temperature, and if the temperatures go beyond the saturation, it's evaporation. The solution step is like it. We can solve this fixed equation model by the Gordon method. It's a simple upwind scheme. That's upwind scheme what we studied in computational fluid dynamics. That's similar to that, but it solves the hyperbolic parts, because these equations are much more used with the hyperbolic part. For the solver, we use the Harten lags when we contact scheme for solving the intercell fluxes. Intercell fluxes is a much more related with the numerical method. Okay. And this scheme we solved. I am not going very details about this. I am highlighting the solution method. That's pressure relaxation, temperature relaxation, or thermal relaxation, and chemical relaxation. Pressure and temperature relaxation we can provide our interface, all the fields also, the liquid phase and gas phase. Temperature and chemical relaxation we restricted to apply only the interface. We are not applying anything beyond the interface, because in experiment we've seen that the evaporation is taking place at the interface only, not beyond the interface. That's why we apply this chemical relaxation or allow to phase change at the interface only. The phase change, we check the temperature. If temperature is higher than saturation point, evaporation will take place, phase change will take place. For the boundary condition,
As we know that tube length is fixed, and this one side is open, another side is closed. And for the bottom side, we use the reflective boundary condition. Upper side is we use the transmittive boundary condition. Okay, that these boundary conditions are there. Now the solution for the mechanical relaxation. The mechanical relaxation, how we solve that mechanical relaxation? Mechanical relaxation, we only take the time-dependent terms in the left side, the hyperbolic equation, and the mechanical relaxation parameter. We solved this and comes out with the one algebraic equation having one unknown parameter, that is the pressure. What is the common pressure in the interface? And we solved it for the common pressure and find out the volume fraction. That's new relaxed volume fraction. Okay, whatever we calculating after calculation of after performing the relaxation, we call the relaxation pressure, relaxation volume fraction, relaxation temperature. Now, this thermodynamic equilibrium means all the relaxation, mechanical relaxation, thermal relaxation, and the chemical relaxation. After solving, but the solution process is like that. Mechanical relaxation is fast because it's very fast. The pressure relaxation is very fast. Then temperature relaxation. Then coming to the chemical relaxation. Okay, we are not going the reverse way because the pressure relaxation is something is different pressure is coming very shortly is a one common pressure. But there is a temperature difference in two systems. It will take slightly higher time compared to the pressure relaxation. Okay, these two chambers are there. Different pressure, you mix it by rupturing the barrier, it's very quickly it's come to the one pressure. But if a different temperature fluids, you have remove this barrier, it will take more time to make one thermal equilibrium condition or it's a one common temperature. That's why the solution procedure is like that. First mechanical, thermal, and then chemical relaxation. And we solve as an interface only. If you plot the volume fraction of the liquid, because X is the distance, we already seen here. This at the left side is a liquid state, right side is a gas or vapor state. In between there is a diaphragm. Then in this intermediate or is a diaphragm near to the interface, we can see that is a not very sharp. Is we use this particular model is a diffuse interface model. In the diffuse interface means there is no sharp jump in pressure, volume fraction like that. Okay. There is a diffuse means a slow diffuse terms like that. It's a diffuse interface that we call the diffuse interface, and we at this interface we only solve this thermal and chemical relaxation. Next things are there. So if you see that all the what is available in literature up to 2017 I just collected. There is a numerical model to solve it. Different model 5, 6, 7 equation model, even sharp interface method they use. That solving method for the two-phase flow or interface problem. There is one is diffuse interface, another is sharp interface. There are separate advantages and different disadvantages of this model. I'm not going to discuss about the detail about this, the sharp and diffuse interface. But if you see the literature, that front propagation with the nucleation site is the rear. Nobody starts simulation what will affect when nucleation site is there. But these things we already seen the experiment. That's why we are interested to perform the numerical. Then for putting the nucleation site, now this putting the nucleation site in the liquid, because we assume for the we are not going this random nucleation site in the liquid site. We just putting one fixed nucleation site in the liquid. Okay, sorry for it. Now, Then this is a one-dimensional model, and we have to put the one nucleation site in liquid. Okay. For one-dimensional model, we put one gas particle on the liquid side, and that gas particle is having the same density of the gas phase, means is the vapor phase of the liquid. That is, if you are using the Dewangan liquid, then what is the density of the Dewangan vapor, given that property again. And the pressure is same as the liquid Dewangan. Dewangan is a fluid. Okay, we are not using initially is the water. First we validated with the Dewangan, then we go for the water. Then we put it, one gas particle in the liquid side, having pressure is the liquid pressure, temperature of the liquid temperature, but void fraction is the gas, and density we can find by the equation of the state. And different parameters we already seen, and in some literatures, that is different parameters, that gamma and this P infinity. Okay. Then density we can find it and just give the density of this gas particle, and we assume this particle as a nucleation site. This way we can mimic the experiment thing. Not exactly, but we can mimic the experiment things. We put it one fixed nucleation site in the liquid phase. Now, the numerical parameters is like that. We perform the and we just put the one interface is a 0.75 meters from the left end. Okay, it's nearly this point, and we use a 1000 cell, and we use a 1 meter length of the domain. CFL we are taking 0.9. Density of the vapor we calculated based on the given pressure and temperature. The density of vapor Dewangan is 0.0059. Okay. That is all are in SI unit, that's the kg meter cube, and the liquid density of Dewangan is the 480.72. In the right side property is like that. Okay. And the nucleation site properties we calculated from the equation of the state, and the density of the nucleation site that's put in the liquid phase, that is 17.84. Velocity initially, there is no motion in the liquid side as well as no motion in the gas side, then velocity is 0. Pressure we are giving the 5 bar of the liquid side, and with 100 pascal to the vapor side to mimic the vacuum. Temperature we are giving, the left side is a liquid side temperature we are giving is a 570 degrees the Kelvin, and is a liquid side we are giving 300 Kelvin, like 27 degrees. Void fraction, this is a two-phase, two-fluid model, and this model we give the two-fluid model means in the
Participants, I request you to not leave the meeting. As soon as the technical issue resolves, sir will join again and start presenting his work. Please be with us.
Okay. Sorry for interruption. I think time is also less. Then I have to conclude with that. Okay. This simulation is a one-dimensional simulation. This kind of simulation video you already seen in shock tube analysis. That's one dimension. How pressure, velocity, mixture density, and volume fraction is changed interface. But this is different because this evaporation is also associated here. And this simulation is up to 10 milliseconds. It's not very high time. But the simulation is taking too much time because time frame or time step is very, very less. And this we can see that how nucleation site is restrict the propagation of the evaporation as well as this expansion wave, and how evaporation will take place near to the nucleation site. Here is a nucleation site at 0.7 meters. Okay. Now you can see there is a lot of oscillations of pressure between the nucleation site and the primary interface. Primary interface means is here at 0.7 meters on the surface. Now, as the left side is a reflective boundary condition, then pressure wave goes to the left end and is reflected to the nucleation side. And again, nucleation side is it's passed some pressure wave through the nucleation side and reflected from the left end. Again, it's oscillated between the left end and the nucleation side, because the nucleation side is a low speed of sound compared to the liquid. then it's not allowed to pass. Like I said, work as a barrier. Now, and this point we can see that is in between the nucleation side and primary interface, evaporation will take place. Okay, and front is propagating, but we are not here saying we are not clearly seeing here how front is propagating vacuum. But more or less we can see the pressure oscillations between the left end and between the nucleation side. And this is the different wave, wave velocity we can see here. The liquid interface nearly is going to beyond the 100. And the left end, this numerical simulation is not clearly predicting, because the left end we can see there is a liquid white fraction is decreased, but in the experiment it's not. That because of this point, the delay time is important. As I already said that the delay time is important, and if we are not able to clearly predict this time, the delay time. If we know the delay time, then we can restrict the simulation to take the evaporation after some delay time. But this simulation is not understanding, like, okay, as the pressure is decreased, it starts the evaporation. But the experimentally this is not happening because of some delay time. So what it will take fraction of time, then it starts. Okay, then we perform the experiment. The nucleation experiment, and we see that the nucleation site is superimposed image. We can see the nucleation site, how its growth and how front is propagated. And this growth of nucleation site is very high compared to the propagation. That's already seen in different image also. Here also, and we perform the same water for the here for simulation, and we compare it. We are not quantitatively complete. We qualitatively we compare it, how this front velocity, how the growth velocity. After that, the merging of this bubble and the front. Then again one new interface is formed. Then how it's propagated. This is a numerical simulation result. That is a primary and secondary interface velocity. The primary front velocity is your interface velocity. Secondary means your nucleation growth. You can see the secondary. That is a versus time. And we can see here that three different primary front velocity, nucleated phase velocity, and primary front velocity after the collapse. And the primary front velocity is very less. We can see the 6 up to the 6 meter per second. Then the nucleated phase growth velocity, if you are saying that it's going up to near to 350 meter per second. That is the growth rate of bubble. That is a very high. Growth rate of bubble, we already seen the growth rate of bubble is very high compared to the front. Then after that merging of these two, okay, the thin film is formed, and this merging or evaporation of this film, again front is to start propagating at the end of the nucleation site, and that velocity is slow. Okay, I am not going to show these things. That's I will come to conclusion parts, because time is we have to stick, because some time is left for the question. Okay. Nucleation ahead of flashing point effect is propagation velocity. As we already seen that if nucleation site is there, it's affect the propagation velocity because it's work as a barrier to pass the expansion wave through it. The nucleation site. The presence of nucleation site hinders, NS means nucleation site, hinders the propagation of expansion wave as well as propagation wave reflected in from the completion domain in the reverse direction. Both causes reduction in propagation. Okay, if nucleation site is there, it reduces the propagation velocity. Next is the growth of nucleation site, growth in nucleated phase. We already seen the this experiment. This speed is very high compared to the front. And if the location of the nucleation site is again is affecting the nucleation site. And we already seen the multiple. If at a time there's more than one nucleation site is there, then it's what is the effect of that. But this is a limited study. In future, maybe that's much more study will come to give the 2D and 3D analysis of this about the classification. Okay, is there any question? Hello?
Moving forward with the Q&A session, I request all the participants to type their questions in the chat box.
Good morning, sir.
Good morning.
Sir, I have a doubt. So, why isothermal line is not straight in wet region of PV curve in flashing front?
Yeah. Actually, we studied in undergraduate, that's thermodynamics, or even heat transfer book. If you see, the line is
Sir,
straight.
actually, why
But
isothermal line? Yes, sir.
yes,
Sir, am
yes,
I
yes.
audible?
That's I'm coming. Yeah, yeah, yeah.
Okay, sir. Thank you.
Then it's not constant, because if you perform the experiment, you can see there is a time when temperature is below the saturation point, means the liquid becomes superheated. Then it still is not directly. Sorry. Its liquid is not evaporate quickly. It's not evaporate, means pressure and temperature both not remain constant, okay, experimentally. But in the for simplification process,
Okay,
we
sir. Thank
all
you.
seen that is okay, it's a
Yes, sir.
pressure and temperature is constant. But actually, if you perform the experiment, you can observe these things. And this experiment is same thing. We already measure it. Its liquid becomes superheated. Okay, then we can see that temperature is vary. Okay, and pressure is also vary. It's not constant in the two-phase zone. The experiment, the actual things are there, but if you perform the experiment very critically, if you're seeing superheated liquid, then you can observe these things. Okay, but this is true. Okay, for simplification process, we are not studying this thing in undergraduate level. Okay, but this is actual. Yeah.
Thank you so much, sir. Sir, we have a question from Mr. Kishore Kumar Sahu. He asks
Yeah.
how the material of tube will affect the phenomenon.
Material of the tube is also a good question. Material of the tube, also we thinking that material of the tube is a very phenomena. It's a greatly affect, because we particularly for this experiment we use borosilicate glass, very smooth surface borosilicate glass, and we try to suppress the nucleation site. If we change the material, that is the borosilicate glass, to another glass that have a rough surface, then it's offered the number of nucleation sites, then we will not suppress the nucleation site, and we will not clearly observe this kind of phenomena. And if you go for the metal tube, then it's again is a metal is, if you contact metal contact, then is again is a number of nucleation sites from the metal. And if you start the uh, process, is only the nucleation site is coming, no front will be found. But this, the correct is, this material is actual things, because we are not supplying the liquid in glass tube. The glass tube is only we used for the visualization purpose. The actual things are metal tubes. We have to flow the water or other liquids. Then it's obviously it's affect the phenomena. It's, but it's a material. We can go different material, means it's only affect the nucleation site only. Yeah.
Thank you so much, sir. Sir, we have another question from Ms. Bhavya Besre. Sir, the question is, what are the drawbacks of cavitation phenomenon and why do we want to eliminate it?
It's not always to drawbacks of cavitation, because the cavitation used in medical line, that's a different treatment. That's kidney stone treatment is based on the cavitation. Okay? It's not always the drawbacks. And even the by the cavitation, uh, that's new technologies coming with different applications with the cavitation. It's not always we can say that the cavitation is drawback and disadvantage to us. We eliminate where we not want the cavitation. Means when, just like we are thinking something, some place cavitation is beneficial, some place cavitation is not beneficial, is harm to our devices. Then when there's cavitation in the valve or cavitation in turbine blade, it erode the turbine blade and erode and destroy and damage the valves. That's why we eliminate the cavitation on these uh, places. Otherwise, no need to eliminate the cavitation. If cavitation giving some benefit to us, why we need to uh, eliminate it? Okay. Yes.
Thank you so much, sir. Sir, I have a question. Sir, can the
Yeah.
phenomenon of flashing in liquids be naturally induced?
Yeah.
Obviously, yeah, naturally it's induced, but it will make a systematic. Yeah. Liquid is not exactly liquid, but this process is not possible. There is a sudden depressurization of the liquid is directly not possible. But the volcano eruption, if you are seeing the volcano eruption, this the fluids, like it's not. We can say that it's a liquid, like it's a very viscous fluid that is coming out. Okay, it's coming out inside high pressure, it's coming out to low pressure. Then sudden that's volcano eruption we can see. This I think is a one example if you're seeing this phenomenon naturally. But simple water or liquid we can't find it. I think it's or naturally it's not possible because how it's suddenly pressure changes. But some places may be there, depends on the earth geometry or condition, maybe it's possible. But one example, I think this volcano eruption only. Yeah.
Thank you so much, sir. I request all the participants to type out their queries if they have in the chat box. And meanwhile, while we have the questions, sir, I would request you to share your presentation so that we can
Yeah.
share it with all the other participants.
Yeah. Yeah. Okay. 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 I have to make it PDF so that I will send it.
Yes, sir. Sure,
I
sir.
will. Okay. I think later I will send to you.
Yes, sir. Sure, sir.
Okay. Any other question?
So I guess this is the end of the Q&A session. Now I would like to express my gratitude and heartiest thanks to you, sir, for sharing with us your experience and knowledge. I wish all the participants learned a lot from today's session and would take back new perspectives with them. I wish you all a good and safe day ahead, and we are grateful to have interacted with you, sir. Thank you, sir, for joining with us.
Okay. Thank you. Thank you. Thank you, Rao sir, and thank you, Sharma sir.
Thank you very much, sir. Kush sir, thank you very much.
Okay. Okay. Thank you. I will share this PDF to Sharma sir.
Sure, sir. Sure.
Okay, but you can give some time to make this
Okay,
systematic so
sir.
that I
There is
will.
no problem. There is no problem, sir.
Okay.
Thank you very much.
Okay. Thank you, sir. Thank you. Okay.
So this marks the end of session 1. Please stay with us and we will connect again at 12 p.m. for the second session of the day with Manoj Yadav, sir. I repeat, participants, we will connect again at 12 p.m. for the second session. I beg your pardon. We will connect again at 12 p.m. for the second session with Praveen Shukla, sir. Thank you.